Good morning. So this is the first time I'm attending PyCon. This is also my first technical conference. I usually attend scientific conferences wherein we would present really much geekier stuff. I'm a physicist by training. And ever since I returned from Singapore, I've been talking to a lot of businessmen and managers and C-level execs, and of course students who would want to go into data science, but not this kind of crowd, right? So are all of you developers? I don't really know the profile. Who here are developers? Cool, so I need your help. I'm not a developer, okay? So in January 2006, just a bit of context, because I'm going to talk about scientific research. So this is not going to be purely Python, but how Python has been helping me and my colleagues perform scientific research, and especially the community, how you've been helping us, right? In January 2006, I graduated undergraduate, I think, from the University of the Philippines in Diliman. I was doing physics. I was with the National Institute of Physics and went on to pursue a PhD. And in January 2012, Singapore government went to UP and they said, why don't you join our team at the Agency for Science, Technology, and Research, that's A-STAR. So I was with A-STAR, which is a government think tank. We did a lot of modeling and simulations, and I was there for 5.5 years until July of last year when I joined AIM. So a lot of people ask me why, right? Especially since at the Institute of High Performance Computing, we're now, at that time, we were building an AI team, a big AI team, an entire department. And then I decided to join AIM. Well, because we're going to start the very first data science program in the country. So I thought that was very relevant. Do you agree? Yes. All right, so July 2017. So why am I showing you this for this talk? I am not a programmer the way you would define it. I use programming languages to achieve certain goals, like do research. So when I was in third year college, that's the only time I learned how to code. I started learning C++. And then you will see later why I transitioned from C++ to, of course, Python, our favorite language, right? And this is also why the data science curriculum will be taught in Python purely. Okay? All right, so scientific research. I'm going to talk about, is this okay? My research field, complex systems? Okay? All right. So complex systems is a relatively new field. Okay? It's, in general research, if you define it, it tends to be used to characterize something with many parts that are highly interacting and in intricate arrangements. So examples of these complex systems: school of fish, flock of birds, even society is an example of a complex system. Complicated versus complex. This is an example of a complicated system. You see the airplane, there's so many parts, it's very complicated, but you know the function of each individual part, right? You remove one part, you know the effect. Agree? Yes. So, but if you talk about complex systems, this is air flights network. So each of the dot there is a airport, and then the link is a route from one airport to another. Now, if you remove one airport, what is the effect? It's unpredictable, right? It's difficult to really predict what exactly would happen. So this is an example of a complex system. There's a lot of complex systems in nature. Like, for example, here the movement of the fish, the birds. This one here, I like this example, ant bridge. Like, how do these ants form the bridge, right? Do they talk to each other? Is there a leader? So these are some of the questions that we ask in complex systems. But when I was in Singapore, we were interested in the science of cities. So when you talk about cities, that's a classic example of a complex system. Have a look at this one here. That's traffic, right? It's chaotic, yes, but there are no accidents. This is an example of a complex system. One of the things that we ask here is, what if I put a traffic light, right? Will it improve the system? No? You don't think so? Probably not, right? It will just add more chaos and delays. So this is what we call self-organization. Example of complex system is also the stock market. You know, all the different traders, they all decide, and based on their decision, it will affect the decision of other people. So it's difficult to build these complex systems. Promise I'm going to get to Python later. Okay? So the field of complex systems covers a lot of topics, from demographic change to financial and economic stability, public health, spread of epidemics, collective social behavior, all the way to reliability of critical infrastructures, which was our focus when we were in Singapore. There's a lot of different fields that are involved there. And you know this guy? Who's that guy? Stephen Hawking, yeah. So proud. He says that he thinks that the next century will be the century of complexity. So even before I got into data science, which I think is just a label, I was doing complex systems research. I still am doing complex systems research. So the basic idea there is that you cannot study a single system by isolating it from the whole system. So if you want to study traffic, right, you also need to understand land use design. Do you agree? You also need to understand the economic activities of individuals. So it's something like this. The whole is more than the sum of its parts. Now, if you're doing this kind of research, are you still with me? Have you had your coffee? Okay. I think there's coffee at the back, right? There's a lot of different maths and science involved there. Okay? That's why our team here at AIM and also in Singapore, it's a combination of different backgrounds. We have engineers, computer scientists, statisticians, mathematicians, and myself, a physicist, to study one single system. All right? So it involves like pattern formation, evolution, and adaptation. This is where AI would come in, and this is where machine learning would come in, network analytics, etc., etc. So when we were in Singapore, understandably, hopefully next year, if I get to talk as well, I get to talk about our projects here. I just returned, so the examples would be from Singapore. Okay? So these were some of the projects that we did. As you can see here, can you see from the back? We did crowd modeling and simulations, modeling and simulations of the rapid transit system, which Beato has seen many times. Dynamical model of Twitter activity profiles. When we did this research, most of the time, we were coding in Python. Okay? So we were coding in Python. Now I'm going to discuss one specific project that helped me transition from using C++. I was very impressed with C++. I loved it. But then this specific research problem that I did really convinced me that Python, for a scientist like me, for a researcher like me, is the language to use. Okay? Are you familiar with this statement? Sorry for those who cannot speak Filipino. Maybe you can ask your seatmate, right? Open-minded ka ba? Tara, kape. What's this line? What? Network marketing, pyramiding. So, not really pyramiding, multi-level marketing, okay? So, this was the research that I did. I had to build simulations of multi-level marketing. So when you do this, right now, most of the kids, when we talk about modeling, all they know, really, is like machine learning, right? Deep learning. But there are a lot more other ways to model systems. All these modeling, like machine learning, deep learning, is just one side of it. Before I did all this neural network research, I was actually doing agent-based modeling. Who's familiar with agent-based modeling? Oh, only a few. Really? It's mechanism-based modeling. I will show you some examples later. So what I did here, I think, in my undergraduate, this was my thesis, I wanted to understand the dynamics behind word-of-mouth marketing, whether or not it's reliable, sustainable, and profitable. That was the research problem that I wanted to solve. So I had to build a society, right? I had to simulate society, social network structure, wherein people can actually recruit other people, right? So I recruit one person, that person will recruit another person. Are you familiar with this? Yes, okay. So for that research, for that scientific research, I had to build an agent-based model, but I also had to be familiar with network science, which is going to be the backbone, the social network of the entire thing, right? And this is the thing with real-world systems like cities or traffic. You cannot write them down in one equation. If you want to model and simulate them, you have to do it algorithmically, right? So may mga rules. This will happen, if this will happen, interact, etc., etc. You have the rules there. So agent-based modeling, for those of you who are not very familiar with the field, is that it's a class of computational models for simulating the actions and interactions of autonomous agents. I think most of the computer science students here are familiar with agent-based modeling. So it's been used for policy making. Especially when we were in Singapore, we were using this a lot. Even the policymakers there are aware of agent-based modeling. Examples where this was applied is epidemiology and contagion, traffic, financial markets. I'm just going to show you some examples to be concrete. The one on your left is an agent-based model of the spread of H1N1, the disease. Okay? They were using traffic network and traffic flights, air flights network, and then they were understanding how people spread and the disease would spread. The one on the right is the one we built for the Singapore transportation system. We built an agent-based model of the entire thing. So this is what I did for the MLM. So first, I built a society, okay? And then from the social network of society, they're going to recruit each other. So how do you build a social network? There's a theory from mathematicians that we are friends by some random chance. Do you agree? Are we friends by some random chance? No. Later I'm going to ask you why. I don't want to go there and ask you. Okay, no, because if we were friends randomly, the distribution of friendships would be Poissonian. Okay, sorry, bell curve. It will be bell curve. But because of data science, they were able to find certain characteristics in social networks that the network of friendship connection is short, there's the short path, and there's high clustering. So what do we mean by that? Short path length means that 6 degrees of separation. Diba? When you see a friend who's a friend of a friend, and you say, oh, it's a small world. So that's one characteristic of a social network. The other characteristic is the high clustering coefficient. What does this mean? That we cluster together. So usually, normally, your friend would be friends with your other friends. Do you understand? Yes. So for this one, there are certain models. So what I did was, I wrote a really, really long C++. So now we're going to Python. So first, I had to build that social network with these rules, making sure that the resulting network is small world, or exhibits a small world phenomenon, the property, and the high clustering coefficient. It took me, because that was my first time in coding, so it took me a few months to really build this. I had to make sure the math was correct. This was tough. And then I defended my thesis. I was, 19 years old, I think. And then the advisor wanted me to generate a certain plot. And I said, I'm not going to write this again. And then there was this friend, very, very good friend, talked about Python. He taught me Network X. All this line of code. Just this. I was like, are you kidding me? All right? So this was, wow, right? Super, super, super wow. So I still keep my code, I want it framed, the C++ one, so that people will say that I actually did understand what the math was, happening behind it. So it was very moving. It was, wow, Python. I love all of you for doing this for us. So for that research, I used NetworkX and NumPy, of course, and Matplotlib. So that's one reason why, ever since I never looked back, it's always been Python from that point forward. So last week, I posted this on my Facebook. It's public, maybe you can see it. I asked my fellow scientists and researchers, like, why are you using Python? Why Python? So some of their responses, I'm going to show it here. The first one, again, the libraries, right? The wide collection of libraries. So why is this important for scientists and researchers? Because really, we don't like to code, to be honest. We just have a hypothesis. We want to model things. We want it implemented the most efficient way possible. Okay? And the developers like you love the code, and you create these libraries for us that we can use. Okay? So that's Python. And another one, it's the community, really. So this was in 2008. Okay, I still got the email. The nice thing with Python is that the community is that you can ask, right? You can ask the developer what went behind that function. Okay, so I emailed these guys. I haven't met them in person. This was back in 2008. And they did reply. I asked them, like, how did you implement this model? Because I'm going to use it in my thesis. I want to make sure that the math and the science is correct. And they would actually reply. I loved it, right? So I was able to build this and eventually build a small simulation like SimCity of sorts, how multi-level marketing really happens. And I was able to show finally in my thesis that contrary to claims of exponential growth, like I recruit 2 people, the 2 people will recruit 2 more, and then 2 more, etc., exponential, it's actually not. It's going to die down after a certain level, okay? And you can find it here. Later we can chat if you're interested in this result. I love this talk given by Jake Vanderplas. I think he did deliver this in PyCon last year. He did talk about the unexpected effectiveness of Python in science. So this is the usual stack that we use, plus. Right? Of course, TensorFlow would be there. It's not there yet, okay? And Keras, H2AI. And for my field of complex systems, again, this is really good because I don't have to code a lot, right? They have this Python-based simulation code repository for complex systems. This is why, really, I mean, if you're not using Python as a researcher or scientist, you'd have to code everything, even the functions. So this is one, so if you're a scientist, you have a lot of ideas, right? You don't have to worry of the code. So I found this graph tool, and what did I do here? I generated this plot of all the Python packages that you will find in PyPy. And what I did was a PyPy dependency network. I really couldn't find the code. I'm really bad at this. But I'll try to look for it if you're interested in looking at it. So these are all the libraries and how they are dependent with each other. What do you think? The size is like how many other libraries are independent or are dependent on you. Sorry. What do you think is this biggest white thing there? It's big because there's a lot of other libraries that are dependent on that. No, malapit na. It's almost. PEEP. PEEP is one of the big ones. No, it's one of the big ones. What do you think? So I mined PyPy, and then I got this. It's actually, I hope someone can answer. I thought they were developers. I'm just kidding. It's setup tools. I don't get it. You're laughing. I don't get it. Anyway. All right, so it's setup tools. Right, so all these data sets you can now analyze and manipulate. And then if you are interested in the dynamics of it, then you don't have to worry about coding this. The nice thing about Python as well is that you can use C++ with it. So the author, the developer of this specific package actually used Boost because when you talk about graph theory, it's very computationally expensive. Okay? So again, I didn't have to worry about that. And this one, I also plotted the different maps. Normally, I would prefer. Can I mention R here? Yeah, is it okay? So I would use that language. But then now we have OSM read. It will allow me to get all the different maps from OSM. But then the plotting, I would still write it myself. And then a month later, I found that somebody developed OSM NX. It's really crazy, right? You just plot this, OX graph from place, you put the place, and then suddenly you have all this. It's beautiful. So if you're a scientist or a researcher, I just used this call, and then we started understanding how taxi dynamics happens, like ride sharing, because I have all this infrastructure. I didn't have to worry about mining all these data and then plotting them and then analyzing them with my own functions. right? You feel me? Yeah. All right, good. Another one, of course, travel DNA. So each of these fingerprint, we call it, is a travel DNA of one person. We were tracking people with their tap-in and tap-out information from the MRT and bus systems in Singapore. And from here, I use these different packages to determine whether that person is adult, a child, or a senior citizen, just by looking at their travel print. Again, the idea was in my head. Good thing Python was there because I don't have to write every single model because it's already there. And of course, the publication would have to cite all these packages, right? So you will see now the trend that in most scientific publications, in the references, you will see the different Python packages, right? Okay. So I'm sure all of you have seen this, right? So it's especially true for scientists and researchers, I guess. It's like import anti-gravity, and then you start flying. Yesterday, I was cramming my slide. I wish that there was an import create slides, but no, I still have to create the slides. Another answer on that question, like why Python, Daniel Stanley Tan said that it's dynamically typed. Do you agree? Dynamically typed, do you know what that means? Yeah? Okay. I don't have to worry about declaring variables and precision. In Python 3, the normal division is floating point division and not integer division, which I think is more natural. Do you agree? Yeah. Tuples functions can return multiple things and swap values, etc., etc. So you already all understand this. I have an example for that one. Remember the agent-based model that I wrote? You can see here, I'm not so sure if you can see, but here I would say double, get ability, double, get disability, bool, 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 int, void, int. But if you write that in Python, then you don't have to worry about the different types, right? And for the lists, like this one, you can put different types within one list, which is good, right? Very convenient. So with this Python code, actually, this specific exact code, I was able to build a prototype for the movement of trains across Singapore. This was a prototype, but it already won IEEE Scale Challenge in Amsterdam. So again, I was more focused on the mechanism because Python was so simple and there's a lot of good people in the community developing all these packages for us. I mean, these things are achievable, right? And I think I'm almost done with my talk. Megan is a computer scientist, so she was asking me if she can comment. So she's a computer scientist. She uses Python and suggests it to scientists learning to code because the basic code is easy to read and understand. I totally agree. The syntax is easier to learn. There are excellent libraries, as you've seen just now, especially for machine learning and data crunching, and the resources are actually good. And this is coming from a computer science professor, okay? And this is what she's saying. And she's already a CS1, so she can do a lot of other, she can understand all the other languages. All right. And finally, I love Python because reproducible science. So I'm not very good with the maintenance of my GitHub because I find it tedious, but promise I will fix it. But you can visit eflegara.github.io. I have some notebooks there that I can share. I love how it's reproducible. In the classrooms, we now use, in the data science program at AIM, all of the lectures, even the mathematics for data science, will be taught using the Python notebooks. And I think Jupyter Lab just got released, right? So anyway, so yeah, why Python? You've seen it. It's simple and dynamic. The built-in libraries is really, really, really impressive. The community is so much more impressive. And the reproducibility and many more. So I think what I would, this is my last slide, I would ask from most of the developers, what I noticed was that the transition from Python 2 to Python 3, some of the packages are not working. So please help us fix it. Right? So yeah, I think this is a really good one. I mean, this is my first time to be at this kind of conference. And I want to take this opportunity to thank all of you developers for making things easier for us scientists. We are learning from you. For our publications, we've started to also post our code for people to actually read and share and reproduce. And yeah, with that, I'd like to thank you all for listening.